Hey guys, in this video I'm going to go over another proof problem, and this one's from a real analysis class. This is one of the problems that you do when you're going over real numbers, and so we're going to use the real number axioms, so the field axioms and the order axioms, if I can write. So for my class I have a piece of paper that has all the axioms and they're labeled A1, etc., 0, 1, and some theorems at the bottom. So I don't have that piece of paper uploaded right now, but in a couple of days I'll upload it and I'll add a link to it in the description box below so you guys can follow along with me. In the meantime, for this video, if I ever use any of the axioms, I will state what they are so you can follow along. Okay, so this problem says let alpha and beta, and I'll just call these A and B, be in R, the real numbers. Prove that AB is less than or equal to A squared plus B squared over 2. So if it's not obvious to you right away what to do with this problem or how to prove it, one thing that you can do is try to get all the terms to one side. And in this case, if you do that, it should make it a lot more obvious what you want to do. So let's first multiply by 2 actually. So 2AB is less than or equal to A squared plus B squared. So we just got rid of the denominator on the right hand side. Now we're going to move everything to one side. So we have 0 is less than or equal to A squared minus 2AB plus B squared. And hopefully you guys can see that this looks familiar. It's what you get if you do a binomial expansion. So this is equal to 0 is less than or equal to A minus B squared. So if you can get to this point, then you see that what you're really trying to prove is that this is true. And if you can prove that this is true, you can, in your proof, really easily take the steps to get to the result that you want. So it's going to be easier for us to prove that A minus B squared is greater than or equal to 0. And then we can actually get to the point in the proof that we are asked to solve. So this is kind of scratch paper where you're working through how you want to approach the problem, and now that we have an idea of an easier way to go about proving this, we're going to start the actual formal proof. So the way I proved it was a little bit thorough. There probably is a conciser way to say the same things that I said, but I just went over everything thoroughly, so I'll go over what I did in my proof. So we know that on the side what we want to prove is that A minus B squared is greater than or equal to 0. Well, first we're going to say that if A and B are real numbers, then A minus B is a real number, so then we can use the real number axioms. So if we think of A minus B as a variable, say x, then we're just saying that x squared is greater than or equal to 0, which we know is true from any basic algebra class. So what we're saying is that the square of a number is non-negative. So let's go ahead and prove that using the real number axioms that we know. So I'm going to say, first we will show that the square of a real number must be non-negative. And I'm going to say, by the definition of an ordered set, if x belongs to R, so x is some real number, then one of the following must be true. If x is a real number, then x has to be equal to 0, or x has to be greater than 0, or x has to be less than 0. And this is an ordered axiom. On my piece of paper, it's 0 or O1. So I will read out loud what O1 is. It says R is an ordered field. This implies that for any A, B, and R, exactly one of A is less than B, A equals B, or A is greater than B holds. So that's what I wrote there. Okay, so that gives me 3 cases. So I'm going to prove that x squared has to be greater than or equal to 0 in the 3 possible cases. So I wrote case 1. So let's say suppose x is equal to 0, then x times x is equal to 0 times x, which is equal to x squared is equal to 0. And this is by theorem 1 if you need to write a proof for that. So theorem 1 says if u is in R, then u times 0 is equal to 0, which is equal to 0 times u. So, and real number times 0 is 0, basically. So we proved that if x is 0, then x squared is equal to 0. Case 2 is suppose x is greater than 0, then x times x is greater than 0 times x. And on the side I wrote because x is greater than 0, this means that x squared is greater than 0. And again, I wrote because of theorem 1. Then for case 3, we have suppose x is less than 0. Then we have x times x is greater than 0 times x, because when you multiply a negative, you flip the inequality. So I wrote because x is less than 0. So that means we have x squared is greater than 0 again. And again, because of theorem 1. So then I wrote, by combining case 1, 2, and 3, we have that x squared is greater than or equal to 0. So now that we've proven that the square of any number is greater than or equal to 0, we can say that a minus b has to be a real number, so the square of a minus b has to be greater than or equal to 0, and then we are almost done with the proof. So I said, suppose alpha beta is an R, then a minus b is an R, and this is proven by the axiom A1, so that is, for me, if a, b is an R, then a plus b is an R. And you can also say because a minus b is equal to a plus negative b. So there's another axiom for that. From above, we have that a minus b squared is greater than or equal to 0. Then we're going to do the binomial expansion. So we have a squared minus 2ab plus b squared is greater than or equal to 0. We're going to move 2ab to one side. And we're going to divide by 2. And this is equivalent, if you want to get it exactly to the correct order that we have been asked, we can say that that's equivalent to ab is less than or equal to a squared plus b squared over 2. And we are done with this proof.